Okay, so what I'm going to talk about is integration. And I'm not a math teacher, so I'm not going to go through all the basis of integration, but I do want to talk about what the concept is, okay? And the concept of integration, you're going to hear this in your math class a lot. It's how to find the area under a curve. Meaning the area between the zero axis, the origin, and a function. So I've got this function, and if we wanted to find the area, let's call this A and this point B. If we wanted to find the area under the curve here, in other words between here and here, I don't want to shade it in, maybe I will lightly. If I want to find this area in here, I would use what's called integration. I would find the integral of that function. So this y is some function of x. And what we want to do to find that, we actually want to add up, just, you know, you think of when we had differentiation. What you tried to do, let's take the same kind of thing. If you wanted to find the slope there, you took 2 points and you found the delta x, the delta y, change in y, and divided by the change in x. The rise over run, and you tried to make delta x as small as you could possibly do. And as delta x approaches 0, you would get a very good approximation of the slope by finding the derivatives. We call that differentiation. Integration is a similar kind of process. And again, I'm not going to go through all the mathematical parts of it, but it's based on this. If we could divide this into a whole bunch of little slices, and let me draw one little slice right here. Okay, and if I can find that, I'm going to call that my delta x. If I could make these slices, a whole lot of different slices of size of width delta x, and let's just take at that point right there, you can see it's going to be a rectangle. It's not going to follow the curve perfectly. There's going to be a little bit of error right there. But the area there of that little slice is going to be f of x times delta x. So in integrating, what you want to do is you want to make these delta x's as small as possible, and that means that little error up there, that little part of the rectangle that's above the curve, or in other cases it'll be below the curve, will be kind of small. And let me be really careful. F of x1 will be that, you'll be x1 right there, that beginning point there. Again, don't need to know this, I just want to give you an interpretation of what integration means. So what you do is add up all the areas. Add all slice areas. Okay? So if we add up all those little slices between A and B, then we would have the area under the curve there. And let me put the notation for this is that little curly Q there. Looks kind of like an S in a way, but it's just kind of crammed in there. And this is how you impress people, is now that you're taking calculus and you start writing things with an integral sign, it puzzles your friends, and you look a lot smarter this way. But the integral of f of x, and we say from A to B. We want to find the area between those 2 points, from A to B. And we also write the integral of f of x with respect to dx. dx is a little differential slice, I always think of it. It's the differential variable. I always kind of think of it as a slice. It's the thing that we want to minimize, that x. That little d just means we have infinitesimally small part of x. Okay? dx means infinitesimally, very, very small, chunk of x. Let me put it that way. Chunk of x, or interval of x. So we're going to see this over and over. What you've got to do when you're doing integrations is you're going to figure out what variable, in this case it's very clear because we're doing this f of x, you're going to figure out what variable you want very small chunks of. Okay? Now this is the math interpretation. And I'm going to show you in the next video, I'm going to show you the physics interpretation. But for the math interpretation, they have different shorthands. There's a process for solving these. For example, integral of x dx is equal to x squared over 2. Integral of x squared dx is going to be x cubed over 3. So if you see the pattern, integral of x to the n dx is going to be x to the n plus 1 over n plus 1. So in other words, the area, you can do this, these are called indefinite integrals. And for these ones, you always have a constant after it. Indefinite meaning there are no limits here. We're not doing from a to b. This is just a general expression. So if I integrate x to the n with respect to some infinitesimally small slice, let me draw x to the n. X to the n is going to go up kind of sharply like this. Okay, whatever that n is, we take these slices and we add them up. The difference between any 2 points is going to be x to the n plus 1 over n plus 1 plus c. It's just a mathematical construct that can be derived. You'll probably do it in math class. I don't care if you know how to do it or not, because you don't need to. It's this simple. You'll memorize this equation. Okay, x to the n dx equals x to the n plus 1 over n plus 1. In AP Physics C, this is your money maker right here. This is the guy that's going to get you through most of what you need to integrate. Occasionally we're going to be doing something with e to the x, log x, cosine x, sine x. We're going to learn those later on. But for right now, I just want you to understand this process. You can look these things up in tables. In other words, we're going to find out eventually the integral of all these guys with respect to some infinitesimally small slice. If you graph these, you can look up in tables and you can say, oh, okay, this is going to be the integral of each of those fellows. Okay? Now, if we did a definite integral, we wouldn't need this constant after. You would just plug in the initial value of x and the final value of x, and you could figure out what that is. Let me give you an example of that very quickly before we finish. X cubed. Now let's just do x squared. Stick with that. The integral of x squared from, let's say, 1 to 2, the area under this curve from 1 to 2. So we're looking for that area. Would be the integral of x squared dx. So in other words, the integral of f of x times dx from 1 to 2. And we solve that. If we look up here, remember x squared, well, let's do it this way. X to the n, x squared, x to the 2 plus 1 divided by 2 plus 1 ends up being x cubed over 3. Since it's a definite integral, we don't have to worry about that constant out there. It would cancel out. I'll show you that another time. And we write this line here. We're going to evaluate it from 1 to 2. Once we've done the integral, now we put this line over here. That just means we're going to do x cubed where x is 2. So in other words, 2 cubed over 3. This evaluated 2 minus this whole thing evaluated at 1. 1 cubed over 3. And that ends up being 8/3 minus 1/3 equals 7/3. So that would be the area under this graph of x squared.